All right, we've got our last example here, example 5 from the take-home test. And it's a question involving expected value and also involving chi-square testing. There's a spinner and there's 4 sections. They're evenly divided into skunk, $100, $200, or $500. And let me just briefly talk about the example. This is from the 2003 Form B, question 5. And the contestant spins the wheel. If they land on skunk, they don't win any money and your turn's over. If you end up getting a number, you win that amount of money, and then it's your decision whether or not you want to continue. So if you win $500, you could stop or keep on going. So on your next spin, you could get $100, and then you keep on going until you decide to stop or you hit skunk, and then you lose all your money. Yeah, that's basically it. So the question A is asking pretty straightforward probability question. Question A says, what is the probability that the result will be a number on all of the first 3 spins of the wheel? So each spin is independent, so the probability of getting a number 3 times in a row would be 3/4 times 3/4 times 3/4, which would end up being a grand total of about 0.42, or about 42% of the time. For question B, it's asking you to calculate an expected value. And in question B it says, suppose a contestant has earned $800 on his or her first 3 spins and chooses to spin the wheel again. What is the expected value of his or her total winnings from the first 4 spins that they do? So for question B, we're going to make a table up that actually describes what's happening involving the result, the amount of money that they've actually won, and then the probability that they win that much money. So they could win $0. That's a possibility. They've already won $800, so they could land on the 100 section and get $900. They could end up getting $1,000, or they could add to their total an extra $800 for $1,300 altogether. And the chances of them landing in each of these individual areas is the same, 25%. What we want to do is calculate the expected value, which would just be each individual x times the probability of each individual event occurring, and then you're going to sum those all together. So it would be 0 times 0.25 plus 900 times 1/4 plus 1,000 times 1/4 plus 1,300 times 1/4. When it's all said and done, it ends up being 800. So if you're playing it smart, if you actually reached $800, then perhaps it's as far as you should go, since if you keep on continuing, the the expectation is that you're going to end up not gaining anything by spinning again on average if you've already earned $800. Okay, the last part of the question, question C, asks you to determine whether or not the wheel is bogus. In other words, whether or not the wheel is fair. So someone might complain by playing this game enough that, of course it's not a fair spinner, even though it's divided right. Maybe there's magnets, or the board's tilted some way so that people are losing more frequently than winning. And for something that's physical like this, maybe it'd be a little bit tougher to rig it. But for something like a casino gambling machine, like a video gambling machine, obviously computer program that designates it could make it look like there's an equal chance of each of the sections, but in the circuits of the computer, maybe they would know that if you got to the point where the person was earning a lot of money and they decided to go farther, they could actually make it more likely that you end up skunking out and losing in the game. So someone that doubted whether or not this was fair or not actually spun the wheel 100 times over and got the following results. They skunked out 33 times out of the 100, won $100 21 times, $200 came up 20 times, and $500 came up 26 times. It says, based on these data, can you conclude that the 4 outcomes on this wheel are not equally likely? Give appropriate statistical evidence to support your answer. And this is not straightforward. It's not telling you straightforward to do a hypothesis test, but that's how you get your statistical evidence, is by actually loading it up for a hypothesis test. So there's 4 steps involved. The first step is to state your no and your alternative hypothesis. And what we're going to just do is write this out in words, that the population percentage, this is one way to write it up, the population percentage are equal, or percentages are equal to the hypothetical percentages, to the expected percentages. And you can also write it out as, the whole would be that the wheel is fair, that each item is landing on the expected 25% chance of what you see here for the different situations. And then the how would be that they're not equal to, that they're different. And to do that, we end up needing to complete a chi-squared test for goodness of fit. So that's the first step. The second step is to check the conditions. One of the conditions is that each of the expecteds comes out to be equaling at least 1 or greater. And you can see that the actual expecteds for this wheel, which we could write in the corner of each of this chart, would be 25. Those look like radicals, but they're actually squares. So we can expect at least 25 in each area, so the expected counts are all greater than 1. So that's good news. And another thing is that the wheel is, that the spins are independent of each other. So it's not rigged as some kind of some sort of casino video machine. Each time you spin it, you are going to get a 25% chance of landing on each of the areas. And you obviously have a large sample size because you can spin as much as you can actually, as much as you'd actually like. We're going to be conducting a chi-squared test where we can actually set up the significance level. Let's say the significance level at 1%. And you're going to be using a chi-squared test for goodness of fit. Because we have an expectation of what the model should be delivering 25% of the time. You should be ending up in each area. So we're going to see whether or not these numbers, 33, 21, 20, and 26, are far off away from that expected number of results in each of those sections. And to do that, we're going to follow one of the formulas on the exam, which is for expected